Hi, this is Jong-Min Park from the Korea Advanced Institute of Science and Technology, the first author of COMPASS, High-Efficiency Deep Image Compression with Arbitrary-scale Spatial Scalability, and my advisor is Professor Munchul Kim. Spatially scalable image compression is a topic within image compression that allows the encoding of various versions of an image into a single bitstream in a hierarchical manner with multiple layers. By extracting the desired part of each layer, we can decode an image at a corresponding device resolution. Typically, redundancy between adjacent layers is reduced through a prediction method, resulting in higher coding efficiency. However, existing neural network-based methods have a limitation. They only use a fixed scale factor of 2 between adjacent layers. This limitation makes them impractical for real-world applications that require a variety of scale combinations. Furthermore, the number of layers is also fixed, meaning we can only decode a fixed number of versions of the image. To address this issue, we introduce a novel neural network-based image compression network with arbitrary-scale spatial scalability, called COMPASS, and our work comprises 3 significant contributions. First, COMPASS stands as the pioneering neural network-based spatially scalable image compression method that accommodates arbitrary scalable factors and the number of layers. Second, COMPASS demonstrates significantly improved coding efficiency compared to existing methods. Moreover, it achieves comparable or even superior performance in terms of coding efficiency when compared to single-layer coding across various scale factors. Lastly, COMPASS incorporates an interlayer arbitrary scale prediction technique called LIF, which relies on implicit neural representation to effectively reduce redundancy and support arbitrary scale factors. This is the overall architecture of COMPASS. The COMPASS comprises of 2 types of layers, a base layer that encodes the lowest resolution image, and 1 or more enhancement layers that sequentially encode multiple higher resolution images of arbitrary scales. It should be noted that the COMPASS exploits the shared modules for all the enhancement layers. Specifically, in each enhancement layer, the interlayer arbitrary scale prediction module, called LIF, can effectively estimate and reduce the spatial redundancy between the reconstruction of previous layer and the input of current layer for arbitrary scale factor. Therefore, the residual compression module only encodes the resulting essential residues in reconstructing the image with high coding efficiency. The LIF module extracts feature information from the reconstruction of the previous layer and then upsamples it. Next, it generates a color prediction filter using a filter generation MLP that takes the upsampled feature map, a normalized relative coordinate, and a scale ratio between adjacent layers as inputs. Finally, it applies the color prediction filter to the upsampled feature map to determine the RGB color of the arbitrarily upscaled prediction through a simple matrix multiplication. To train the COMPASS architecture, we use a combined RD loss function. Now, let's talk about the experimental results. We conducted 2 different experiments, focusing on 2 aspects: coding efficiency with a fixed scale factor of 2 and coding efficiency with arbitrary scale factors. Regarding coding efficiency with a fixed scale factor of 2, COMPASS significantly outperforms all spatially scalable coding methods and demonstrates comparable results to the single-layer coding. In terms of coding efficiency with arbitrary scale factors, COMPASS also significantly outperforms all existing methods across the entire range of different scale factors. Furthermore, COMPASS even surpasses the single-layer coding for several scale factors. The subjective qualities of the reconstructions by our COMPASS are significantly better than those from the other methods, and especially, the high-frequency components such as edges and textures are more clearly reconstructed. Thank you for listening, and please feel free to leave comments if you have any questions.